This video is on Le Chatelier's principle. Le Chatelier's principle is a powerful general concept that helps you to understand how systems respond to changes in the concentration, volume, and temperature, pressure. It's easier to understand and apply Le Chatelier's principle than to try to memorize a lot of other stuff. The basic idea of Le Chatelier's principle is that if a system's at equilibrium and then it's disturbed, it will counter that disturbance to get back to equilibrium. What you should be able to do after watching this video, you should be able to determine how a system will respond when it's at equilibrium and then the concentration of the products or reactants would change, when the volume was changed, or when the temperature was changed. Now we can state Le Chatelier's principle that if a system's at equilibrium, meaning Q equals K, you should remember Q is the reaction quotient. It changes as the concentrations change. K is the equilibrium constant. It's constant for a specific reaction at a specific temperature. And so if a system's at equilibrium and then it's disturbed such that Q no longer equals K, the system will counter that disturbance to get back to equilibrium. Now, I like using this graph to think about equilibrium. The y-axis is the free energy. The x-axis is the reaction quotient. The minimum is equilibrium. Remember, systems want to go to the lowest energy possible. Now, in terms of Le Chatelier's principle, if the boulder is at the minimum and we push it up the side a little bit, the darn thing just rolls back down. Same with chemical systems. And so things that can disturb the system at equilibrium would be adding or removing product or reactant, changing the volume of the reaction chamber, or changing the temperature. Now you got to remember that because pure solids, pure liquids do not go into the reaction quotient or equilibrium constant, sometimes adding or removing a reactant or product will not change Q. Sometimes changing the volume will not change Q. And so if Q and K stay the same, the system will not respond. Now, changing temperature does not change Q, but it does change K. Again, K is the equilibrium constant. It's a constant for a specific reaction at a specific temperature. Now we can look at a very simple example. So we have silver chloride. If we add 1 mole of silver chloride to 1 liter of water, what happens? And so if we look at the equilibrium silver chloride solid going to silver ions plus chloride ions, the KSP is 1.8 times 10 minus 10th. And so silver chloride is not very soluble. And so if we add 1 mole of silver chloride, enough will dissolve until we get to that minimum, until we form what's referred to as a saturated solution, until the silver ion concentration times the chloride ion concentration equals the KSP, which is 1.8 times 10 to the minus 10th. The rest will remain solid. And so we can imagine that we have the system at equilibrium. We have the saturated solution, which again means that Q equals K. And so we're at saturation, and then we add some chloride ions, maybe adding some sodium chloride solid. What happens right after we add the sodium chloride? Well, Q, given at the bottom of the screen, is equal to silver ion concentration times the chloride ion concentration. And so immediately after we add the chloride ions, Q should increase. And so we kind of push the boulder up to the right. Now, how will the system respond? Well, the darn boulder just rolls back down to the bottom, or some of the chloride ion concentration will be consumed, forming more silver chloride solid to reestablish equilibrium. And so again, this is an example of Le Chatelier's principle. The system is at equilibrium. We disturbed it such that Q no longer equal to K, and then the system responded by countering that disturbance, getting back to equilibrium where Q equals K. Now again, we can think about having the silver chloride solution, saturated solutions at equilibrium. And then what happens if we add silver chloride solid? Well, again, if we look at Q, it's just equal to silver ion concentration times chlorine ion concentration. Pure solids, pure liquids don't appear in the reaction quotient. And so adding more silver chloride solid does not affect Q. And so even after we add more solid, Q equals K, and so the system's still at equilibrium, and so nothing is going to happen. We can add as much solid as we want, and nothing is going to happen. We can look at a little bit more interesting example. We have iodine gas plus hydrogen gas going to 2 hydrogen iodide gas. And so we can imagine that the system's at equilibrium. That corresponds to the concentrations given in the figure on the left. And so what happens if more iodine gas is added? Well, Q is equal to partial pressure of hydrogen iodide squared over partial pressure of iodine and partial pressure of hydrogen. Remember, the form for Q and K is exactly the same, but Q changes, K does not change. And so because iodine's on the bottom, if we make that bigger, Q will go down. And so right after we add the iodine gas, Q goes down. So we're pushing the boulder to the left. Now, how will the system respond to this disturbance? Well, the boulder is just going to go right back down to the minimum. And so some of the iodine is going to be consumed until we get back to equilibrium. Now again, if you look at the left-hand graph, it's kind of cool. You had these concentrations initial, and then we increase the iodide. That's the spike in the iodide, and then some of the iodide consumed. And when the iodide was consumed, the hydrogen had to be consumed, and HI was produced. And then eventually get back to equilibrium, so the concentrations remain constant. Now, if we take the concentrations before the disturbance and the concentrations after they get constant after the disturbance, and we plug those into our equilibrium expression, we will get exactly the same number. And so the system's at equilibrium, we disturbed it, the system counted that disturbance, got back to equilibrium. Again, this is just an illustration of the Chatelier's principle. We can also look at the same equilibrium. So system's at equilibrium, and then some of the hydrogen gas is removed. Right after the hydrogen gas is removed, is Q greater than K, less than K, or is Q equal to K? Now again, Q is equal to partial pressure of HI squared divided by partial pressure of iodine, partial pressure of hydrogen. And so if we reduce hydrogen, that's going to make Q bigger. And so right after we remove some of the hydrogen gas, Q goes bigger. We're pushing the boulder up to the right. And so how will the system respond? Well, the dang boulders are going to roll back down to the minimum. And so if we remove some hydrogen gas, the system is going to produce some more hydrogen gas. Now it's kind of cool again if we look at the plot on the left. And so initially the concentrations at equilibrium, we remove the hydrogen gas. And so you see that concentration drop. And then the system responds by producing more hydrogen gas. Now, when it produces more hydrogen gas, it also produces more iodine gas. So those concentrations go up. And notice that the concentration of HI also goes down. Now, again, if we take the numbers on the far left, and we take for the concentration, and if we take the numbers for the concentration on the far right, and we plug in both sets of numbers into the expression for the equilibrium constant, we get exactly the same value. And so the equilibrium constant is a constant for a specific reaction at a specific temperature. System responded to equilibrium. And so again, if we think about the graph on the right, the boulder was on the bottom in the valley. We pushed it up to the right, and the darn thing just rolled back down until it was down at the minimum again. Again, this is just an illustration of the Chatelier's principle. We can try something a little bit more difficult. And so if the system's at equilibrium, the volume is doubled. Does that make Q greater than K, less than K, or is it equal to K? Now, K is independent of the volume, so we don't have to worry about K changing. Now, Q can change with volume. It actually depends on the number of gas particles in the products versus the number of gas particles in the reactants. Now, looking at the reaction, we see that we have 2 gas particles products and 2 gas particles reactants. And so Q is actually going to be independent of the volume. And so changing the volume will not change Q. Now we can actually prove this to ourselves by doing some math, because math is fun. And so Q is equal to partial pressure of HI squared divided by partial pressure of iodine times partial pressure of hydrogen. Now if we plug in nRT over V for the partial pressures, assuming ideal gas, and then notice that the RTs cancel and the V cancels, and we're left with just a number of moles. And so we see that Q is independent of volume. Now we could also have not canceled the volume and just ended up with the concentrations, Q sub C, but this is probably better. And so Q is independent of volume when we have the same number of gas particles, products, and reactants. And so changing the volume did not change Q, did not change K, and so even though we changed the volume, nothing happened. That when the total pressure changed by changing the volume, Q did not change because we had the same number of gas particles, products, and reactants. Now we can look at a different reaction. Here we have 2NO2 going to N2O4. Now if the system at equilibrium and the volume is doubled, does this make Q greater than K, less than K, or is Q equal to K? Now think about Le Chatelier's principle and thinking about how it wants to counter a disturbance. We can think about this, okay, so if I increase the volume, am I going to want to produce more gas particles or fewer gas particles? Now, if I increase the volume, I'm going to want to produce more gas particles. And so if we look at our reaction, we have 2 gas particles reactants, 1 gas particle product. And so what we should predict is that if I increase the volume, we're going to produce more reactants because that will produce more gas particles and that will counter that disturbance. Now, again, we can do some math. Math is fun. And so Q. Again, we have the partial pressures, and then we replace the partial pressures with nRT over V. And we see that when we do this for this reaction, the V's do not cancel. And so we get Q is actually equal to V over RT. And so increasing the volume actually does increase Q. And so again, it's the Chatelier principle. And so increasing the volume increases Q. And so that means that products will form more reactants until we get back to equilibrium. We can look at another example. So say we're at equilibrium, and then the total pressure of the system is increased by adding neon gas. Does this make Q greater than K, less than K, or is Q equal to K? Now Q does not contain neon gas. Neon gas is a noble gas. It's not reactive. And so adding neon gas should not affect Q or K. And so Q remains unchanged. System does not respond. And so changing pressure does not change the value of the Ekman constant at constant temperature. Solids and liquids and aqueous compounds are not affected by pressure changes. Changing pressure by introducing inert gas will not shift equilibrium. Only when there's a change in partial pressure of the gases that are part of the equilibrium will the system respond to pressure changes. If there are an equal number of gas particles, products, or reactants, pressure changes due to changes in volume have no effect on the system. Now again, all we have to think about is in terms of Le Chatelier's principle. If we're at equilibrium, and then we have a disturbance such that Q no longer equals K, the system will respond, will counter that disturbance until Q equals K again. Now we can again keep on looking at the same reaction, and so notice that it's exothermic. Heat is a product. And so for all exothermic reactions, heat can be treated as a product. Now if the system's at equilibrium and then the temperature is increased, will more products or more reactants be produced? Now again, Q will not be affected by temperature, but K will. K is a constant for a specific reaction at a specific temperature. Now, if you increase the temperature, that's going to change K. Now, we can think about this problem using the Chatelier's principle. And so heat is a product. And so higher temperatures like adding heat. And so we should expect that it's going to push products to form more reactants. And so kind of cool, we can understand how a system responds to a change in temperature by just using the Chatelier's principle. Now, if we form more reactants, will that mean K is larger or smaller at higher temperatures? Well, if we form more reactants, remember K is products over reactants. And so if the reactants gets bigger, that means K will get smaller. And so for all exothermic reactions, the Ekman constant gets smaller as the temperature is increased. And so for this particular reaction, at 273, K sub C is 1299. At 298, K sub C is 169. And so again, for all exothermic reactions, the Ekman constant gets smaller at higher temperatures. For all endothermic reactions, the Ekman constant increases with increasing temperature.
When NO2 is placed in a closed cylinder under pressure, it reacts in part to form N2O4 molecules, and an equilibrium is established. The formation of N2O4 from NO2 is an exothermic process. Thus, heat is emitted when two NO2 molecules form an N2O4 molecule. The reverse process, dissociation of N2O4 into NO2 molecules, is an endothermic process. Le Chatelier's principle predicts that when the temperature of the equilibrium system is increased at constant volume, the equilibrium will shift in the direction that absorbs heat. This means that more N2O4 molecules will dissociate as the temperature increases.
So just like I mentioned, for all exothermic processes, heat can be treated as a product, and so increase in temperature will cause the Ekman constant get smaller. For all endothermic processes, heat is a reactant, and so increasing temperature increases the Ekman constant. And so Ekman processes are dynamic, they're reversible. Here we have a cobalt complex with water and chlorine, and we notice that if we remove two water molecules from the complex, we get a blue complex, and it's more stable at high temperature.
At room temperature, a solution of cobalt chloride is pink in color. When we heat it, it gradually turns blue. If we then cool the solution in an ice bath, it turns pink again. The reaction reverses.
And so kind of cool, we can actually go backwards and forward just by changing temperature. And so the pink complex is the more stable complex at low temperature. The blue complex is more stable at high temperature. And so high temperature is the reaction below delta G naught is less than 0 and K is greater than 1. At low temperatures, for the reaction below, delta G is greater than 0 and K is less than 1. And so at low temperatures, it's reactant favored, high temperatures, product favored. And so one question we could ask ourselves is the reaction written at below, is that exothermic or endothermic? Now again, if we think about it, if the product is more stable at high temperature, it must mean that heat is a reactant. Adding heat, higher temperature, pushes it towards producing more product. And so that reaction must be endothermic. And so for all endothermic reactions, higher temperature corresponds to larger equilibrium constant. And so it's kind of cool the way of thinking about it. And so we have the plot on the left for low temperature. The minimum is closer to the reactants. And then as we increase the temperature, that minimum actually moves towards the right until it's closer to the products. Notice that as we increase the temperature, the energy of the reactants increase and the energy of the products decrease relatively. And so again, for endothermic processes like this, higher temperature always means larger equilibrium constant. For exothermic processes, higher temperature always means smaller equilibrium constant. And so Le Chatelier's principle, it's way cool. It's very important. Again, it's a very powerful general concept that will help you understand how systems respond to changes in volume, temperature, pressure, etc.